Hey, hello everybody. I'm back. So in this movie clip, let's begin with thermal velocity. So the concept of thermal velocity is how fast or how slow electrons in semiconductors are moving, at which the electron is moving around the crystalline silicon material. To answer this question and this curiosity, we're gonna use a we're going to estimate the average, not single, average electrokinetic energy because for a given temperature, we can estimate the total amount of kinetic energy. Okay, so this equation comes from the ideal gas stuff. Okay, in chemistry, general chemistry, you may have a chance to hear and learn about the ideal gas. Okay, so for a given temperature, the total amount of kinetic energy can be evaluated depending on the temperature. So this silicon material is exposed at room temperature, say 300 Kelvin, then you can plug in the 300 value into the heat. Then we're gonna have an average kinetic energy of electrons. And on the right hand side, you will see the very conventional and typical equation to explain the kinetic energy, 1 over 2 times mass times velocity square. Okay. So because the electron is existing in semiconductors, we're going to use effective mass instead of mass. Okay. And because the energy resource of the electron's movement in silicon material comes from thermal, most likely. So thermal velocity has been denoted as V sub th. Okay. That it indicates a square. So now we are ready to estimate the average thermal velocity of electrons in silicon. Let's do that. So from this equation number one, you can rewrite the equation with respect to thermal velocity V sub th. Okay, and you're gonna get this equation from equation number one, then plug in the values kT and Mn asterisk. Okay, so here Mn times mass, right? 9.1 times 10 to the minus 31. And the KT is, thermal energy as we have learned it, 0.026 electron volt. But instead of one electron volt was equal to 1.6 times 10 to the minus 19 joule, right? So this term has been included here to cancel out the electric volt to have a energy unit joule. Then joule over divided by kilogram is identical to the meter per second. Okay, then we're gonna end up with this number. But in device physics, instead of using meter as a length indicator, we would prefer to use a centimeter as a length indicator. So centimeter per second has been used as a velocity unit, and the value is 2.3 times 10 to the 7 centimeter per second. So it's almost 10 to the 7. Okay, so it's almost uh, half of the population in Korea. Okay, approximately half. And in Seoul Metro City and Gyeonggi Province, about 2 point, I guess, 2.7 people are living in near the Seoul and in Seoul. Okay, so that would be a good hint how fast the thermal velocity of electron in silicon material is. Okay, remember that the main site of SK Hynix and the Samsung Electronics Company, those two major, DRAM makers and NAND flash makers are located in Gyeonggi Province. Okay, so approximately 20 million centimeter per second. That is a thermal velocity of electrons in semiconductor, but by accident, it is quite similar to the total number of people living in Gyeonggi Province and Seoul. Right. Next topic is carrier scattering. Now we are studying how the electrons and holes are moving around in silicon material. Then the the playground of now I'm talking about the of playground for electrons and holes. There are a bunch of electrons and holes are created and they are moving. But what is the playground for them? Definitely crystalline silicon material. Okay, so in this playground, electron holes are moving around. What would be the events that you are expecting? Maybe this electron would hit the silicon atom. Okay, that is the main event to be happened. So in real, that kind of event has been happened for sure. So mobile, movable electrons and holes, electrons and holes, and atoms in silicon lattice means simply silicon atoms, right? Consisting of silicon crystalline material. You know, so silicon atoms and electrons are what? Always in random thermal motion, which means this electron is moving like moving randomly. It is moving right hand side, left hand side, upward, downward. We have no idea what is the next action. We can say that the electron is randomly moving. What about this silicon? Well, this silicon is, tied with the full neighboring silicon atoms. However, this silicon atom itself may be up and down or front and backside and left to right or right to left. It is vibrating. It cannot be pinned at a specific location. It is like a trembling, vibrating. So we can say that the silicon atom are always in random thermal motion. Well, in terms of freedom, degree of freedom, the free electron is more has a higher degree of freedom in terms of movement in the silicon lattice material. However, the silicon atoms is atoms themselves are still moving, but with a very small amount of degree of freedom. Okay, so now the main event, as I told you, the electron is going to hit the silicon atoms. So electrons make what frequent collisions, hit, simply speaking, hit with vibrating atoms. So what are they? Vibrating atoms. That is silicon atoms. Okay, but in using jargon, professional words of solid state physics, that is named as phonons. Okay, so here is a phonon. Phonon is indicating vibrating silicon atom. Okay, so this phonon is collided with electrons quite often. Okay, so once this event, as I told you, a electron is now hit the silicon atom. This event is named as lattice scattering or phonon scattering. Yes, so phonon scattering is more widely used. So phonon scattering can be happened in silicon material. Once at least a few electrons and holes are created. But as we have learned, at room temperature in pure silicon material, how many electrons and holes are available? Did you remember this number for silicon? That is 10 to the 10 per cubic centimeter. Okay, so this number of electrons, a number of electrons, a number of holes are available in crystal silicon material. At room temperature, the thermal velocity of electrons and holes are up to 2.10 to the 7 centimeter per second. So very high speed. With very high speed, from the perspective of human beings, right? 2 times 10 to the 7 centimeter per second is super fast. So at room temperature, with this high speed and the total number of free electron is 10 to the 10 per cubic centimeter. I'm saying cubic centimeter. You know how small this cube, 1 centimeter length, side length, and height, A, A. So all A is 1 centimeter. So 1 centimeter times 1 centimeter times 1 centimeter. This very small, tiny in cube, there is, there are 10 to the 10 free electrons and holes available, and they are moving at a speed of 2 times 10 to the 7 centimeter per second at room temperature. Sounds amazing, right? So this huge amount of electrons and holes make frequent collisions with the vibrating atoms or silicon atoms or phonons. Okay, so these scattering event is named as phonon scattering. Okay, now I hope you to understand the basic and intuitive concept of phonon scattering. Now let's take a look at the next one. Phonon scattering increases. More phonon scattering can be happened when the temperature is increased. At a higher temperature, phonon scattering is more happened. At a lower temperature, a less amount of phonons can be happened. So phonon is proportional to the temperature. So intuitively, if as temperature increases, the amount of vibration of silicon atoms in silicon material becomes higher, becomes more. But at lower temperature, if silicon material is cooled down, then less amount of vibration can be detected and measured. Okay, so your intuition is quite correct. Okay? All right, that's all for the phonon scattering. Now let's move on to the next one. Next one is the other scattering mechanisms. There are the other uh, scattering mechanisms. One of which is ionized impurity scattering, and the last one is carrier to carrier scattering. So most likely the silicon material will be doped with the n-type dopant atoms, donors or acceptors. So it will become the p-type silicon material. So once silicon material is doped with the impurity, then the impurity, as we have learned, is going to be ionized. Ionized means, arsenide is going to donate its fifth electron to the silicon material, so it will become positively ionized, right? And what about the boron coming from the column 3 in periodic table? So it has a total number of outermost electrons for this boron atom is 3. So once it is combining with the 4 neighboring silicon atoms, then once one outermost electron is lacking, so that it is ready to accept a free electron to completely build up the to completely build up the covalent bonds with the 4 neighboring silicon atoms. So it's going to be negatively ionized once it is accepting the free electrons to build up completely the covalent bonds with the 4 neighboring silicon atoms. Okay, so whenever impurity is injected into the silicon material, arsenide is positively charged and boron is negatively charged, so that we can say that impurity atoms are fully ionized. That is the mechanism when we are estimating the total number of electrons out of the doping concentration, donors concentration. Always we are assuming that the donors are fully ionized at room temperature. Okay, but at much lower temperature, the donors, part of the donors are not fully ionized. Okay, watch out and keep an eye on the portion. You remember this figure, right? N over ND versus temperature, and the curve shape is like that, and this temperature region is the extrinsic temperature region, and beyond it is intrinsic temperature region, and this low cold temperature regime is named as a frozen out regime. You may go back to the slide showing and having this figure. Anyhow, ionized impurity atoms are always existing in doped silicon material. So let me switch the color. Okay. So now this silicon atom is switched or doped and placed with the donor atom arsenide, and it is, ionized. Now electron is moving. Then what would be happened compared against when it was filled with the silicon? Originally it was silicon, but now it is arsenide and it is ionized. And now suppose that electron is moving here. When the silicon atom is placed here, the electron is moving toward the right hand side without any, blocking. However, since this silicon atom is now replaced with the arsenide, which is ionized, so once a negatively charged carrier electron is moving in this direction, so it will be attracted toward the positively charged arsenide atom because of the Coulombic force here, Coulombic force between carriers, not between carriers in this case, between ionized atom and electron or carrier. Because of this, Coulombic force between electrons or holes and silicon atoms, or no, no, not silicon, and ionized impurity atom, the trace or direction of electron or holes are modified, resulting in a unexpected collision. This type of collision is named as ionized impurity scattering. Ionized impurity scattering, or simply impurity scattering happened. Okay. So previously I said a phonon scattering. So here the word in front of scattering indicates the root cause of the collision event. So phonon is now causing the scattering of electrons and holes. And in this case, impurity is causing the scattering of electrons and holes. Okay? So impurity scattering or ionized impurity scattering is the second mechanism how the carriers such as electron holes in silicon material has been scattered out. Okay. The last scattering mechanism is described here, carrier to carrier scattering. We always talked about the collision between carriers and the silicon atoms, but we have missed the scattering event between these carriers. Okay, so electrons and electrons. Think about how many electrons are existing within 1 cubic centimeter, 10 to the 10. Huge, right? Humongous number of electrons are available in cubic centimeters. So there is probability of, you know, heating event between two electrons. So this electron to electron scattering is named as a carrier to carrier scattering. And this carrier to carrier scattering is very significant when at high carrier concentration, meaning that at degeneratedly doped silicon material, and you know the meaning of degeneratedly doped. Degeneratedly doped means a very heavily doped silicon material, the electron-electron or hole-to-hole scattering can be significantly happen. Because of what? Because of the total number of electrons and holes are huge. Why they are huge? Because you doped very heavily silicon material. Okay. All right. Okay, that's all for the carrier scattering events. So in summary, there are three primary types of carrier scattering. Number one, phonon scattering. Number two, ionized impurity scattering. Number three, carrier to carrier scattering. Okay, remember and review what the three different types of carrier scatterings are in silicon material. Okay, and the last message in this slide is the net current in any direction is zero. This is very important. We are saying that the electron or hole is moving around the silicon material. And now we have learned what kind of scattering events can be happened. But whenever we are seeing the positively or negatively charged carriers are moving, we can expect any tiny amount of electron or hole can create a very tiny amount of current, right? Because the charged particle is moving. However, this net current, if we sum all the actions coming from each electron holes, so all of the summation of uh, charged particles movements can give us nothing. No really net current can be formed, even though there are a bunch of movement of charged carriers such as electron holes are moving. Okay, so but here one condition is unless electric field is applied. Okay? Unless electric field is applied, the net current in any direction, upward, downward, left, right, up, front, backside, is zero. Okay, so that is the reason why you didn't power up your smartphone. Smartphone cannot work at all because there is no net current flow in integrated circuit. Okay, all right. So I guess it's a good timing to have a short break time here. So I will be back in the next movie clip. So please have a short break time by yourself. And if you need any question, leave your text message, not message, your message in iCampus or join in the WebEx office hour every Tuesday, 3 p.m. TA and TA or I will be there. They are available only for you. So join in the WebEx office hour at 3 p.m. every Tuesday. See you in the next movie clip.